We are now going to discuss a more efficient algorithm to approximately find an eigenvector for the second smallest eigenvalue of the Laplacian of a graph. And for this discussion, we will assume G to be connected, because if G is not connected, then we can find in linear time, using depth first search, two different connected components of G. And from there, we can find an eigenvector orthogonal to the all one vector of eigenvalue 0. So if G is connected, and we consider the space of vectors that is orthogonal to the all one vector, then on this space, L is an invertible linear transformation, because on this space, all the eigenvalues are strictly positive. Being an invertible linear transformation, it means that it has an inverse. So there will be some matrix L plus, which we call the pseudo-inverse of L, such that L plus inverts L for all vectors x that are orthogonal to the all one vector. And L plus will output 0 on the all one vector. And for all other vectors, we can reconstruct the value of L plus by linearity from those equations. The reason why this is an interesting definition is that if 0 up to lambda n are the eigenvalues of L, then the eigenvalues of L plus will be 0 the same as lambda 1, and then there will be all the inverses of the corresponding eigenvalues of L. And the eigenvectors of L plus will be the same as the eigenvectors of L. This means that finding the largest eigenvalue of L plus and a corresponding eigenvector is the same problem as finding the second smallest eigenvalue of L and the corresponding eigenvector. So that applying the power method to L plus would be a method of finding lambda 2. And here is the idea that we want to discuss. Run the power method on L plus, then get a vector whose Rayleigh quotient is going to be maybe not exactly 1 over lambda 2, but say at least 1 over lambda 2 times 1 minus epsilon. And then the intuition would be that if epsilon were 0, then this would be an eigenvector of 1 over lambda 2 for L plus, which would also be an eigenvector for lambda 2 for L. So we may hope that in general, if we find some vector orthogonal to all ones that has this Rayleigh quotient with respect to L plus, maybe its Rayleigh quotient with respect to L should be about this much. And if this whole set of idea really worked out, then if we want to find a vector of Rayleigh quotient, say at most 1.1 times lambda 2 for the Laplacian, we would just need to run this algorithm with epsilon being an absolute constant. While when we run the power method on the matrix twice the identity minus the Laplacian, then we would need the parameter epsilon in the power method to be more like lambda 2 over 20, because at the end we are just going to get the guarantee that our final vector with respect to L is going to have a Rayleigh quotient at most lambda 2 plus 2 epsilon. So if we want the error to be lambda 2 over 10, we will need this epsilon to be lambda 2 over 20. It does make a very big difference if we run the power method with a constant epsilon or with an epsilon that is order of lambda 2, because the running time of the power method is nearly linear in the number of non-zero entries of the matrix, but then multiplied by 1 over epsilon. If epsilon is a constant, this overhead is just a constant, but if epsilon is lambda 2, this overhead becomes 1 over lambda 2, and in some graphs lambda 2 is as small as 1 over n squared, so the overhead would be order of n squared. There are two problems with this idea. One is that in order to run the power method on L plus, it seems that we need to compute L plus, and there is no really efficient algorithm that does this computation. I mean, there are polynomial time algorithms that do this computation, but not nearly linear time algorithms. In fact, it's hopeless to even look for a nearly linear time algorithm here, because it could be that the Laplacian has only order of n non-zero entries, but its pseudo-inverse has order of n squared non-zero entries. So it's not even possible to compute the pseudo-inverse in time nearly linear in a number of non-zero entries of the Laplacian. The second problem is that although this identity is true for eigenvectors, it's not necessarily true for vectors of large Rayleigh quotient for L plus or small Rayleigh quotient for L. So we're going to deal with these two problems. Regarding the first problem, our observation is that if we want to run the power method on L plus, we don't actually need to know L plus. We just need to be able to compute the product of L plus times a vector x for some vector x that we know, and where L plus is the pseudo inverse of a Laplacian L that we know. The product L plus times x is just, for x being orthogonal to the all-one vector, is just the solution y of the system of linear equations Ly times x. And for this problem of solving in y a system of the form Ly equal x, where x is known and L is a Laplacian, is a problem for which nearly linear time algorithms are known, and the most recent of them appears to be also efficient in practice. And notice that by nearly linear time, we mean time nearly linear, so linear up to extra log n terms, in the number of non-zero entries of the Laplacian, so in the number of edges of the graph G. So we are able to compute a vector of large Rayleigh quotient for L plus, given L. But then what is going to be the Rayleigh quotient of this vector with respect to L? To understand this, let's fix a basis of eigenvectors for L, which will also be a basis of eigenvectors for L plus. V1 will be the eigenvector of 0. For the remaining eigenvectors, Vi is going to be the eigenvector of lambda I with respect to L, and the eigenvector of 1 divided by lambda I for L plus. When we apply the power method to L plus to find an approximately largest eigenvalue and an approximate corresponding eigenvector, the output of the power method will be some vector orthogonal to V1 that not only is going to have a large Rayleigh quotient, but if we look into the analysis, it's going to have a property of this form, that when we look at the coefficients corresponding to eigenvalues of L plus that are smaller than the largest eigenvalue by more than a factor 1 minus epsilon, those coefficients they're going to add up to not much. In fact, the sum of their squares is going to be pretty small. Here, this epsilon over n squared could be any polynomial in epsilon and in 1 over n. This will just affect the constant in this big O. Now, since this property is invariant under multiplication by a constant of all the entries, let's scale the entries so that y has length 1. If we make this assumption, then this will be at most epsilon divided by n squared. Now you're ready to compute the Rayleigh quotient of y with respect to L. This will be the summation of a squared times lambda I, which we can break up into the summation for small lambda I and for large lambda I. And let's bound separately the two parts. So when it comes to this part, each of those lambda i's is at most lambda 2 divided by 1 minus epsilon, and then the summation of the ai squared is at most 1, because the summation of all the ai squared is 1. So this part is at most this part. Now let's look at this part. Well, each of those lambda i's is going to be at most 2. This is true for each of the eigenvalues of the Laplacian. So we could certainly upper bound this by taking 2 out. Then what is the summation of this ai squared? That's precisely this summation, because these are the i's that satisfy this inequality are precisely the I that satisfy this inequality. So the summation of those ai squared is at most epsilon divided by n squared times a2 squared, which we said is at most epsilon over n squared. So this part is going to be at most 2 epsilon over n squared. Now lambda 2 divided by 1 minus epsilon is roughly lambda 2 times 1 plus epsilon. And then lambda 2 is always going to be at least 1 over n squared. And so this term 2 epsilon over n square is at most order of epsilon times lambda 2. And so the whole thing is lambda 2 times 1 plus order of epsilon. This means that if we want this to be at most 1.1 times lambda 2, epsilon just needs to be a constant. So the number of iterations in the power method just needs to be log n. So the whole running time is just nearly linear in the size of the graph.